inverse of a function is a function that undoes the original function. So it basically flip-flops all of the x and y coordinates. So if a function has an ordered pair 3, -1, meaning when you plug 3 in, you get -1 out, its inverse will do the opposite. If you plug in -1 into that function, you'll get 3 out. Or if this was our original input, and then we got an output, took that output, and then used it as the input into the inverse of that function, we would end up right back where we started. So the inverse of a function undoes the operations of the original function. So as you can see, we just flip-flop the x and y coordinates of a point. So if we want to find the equation of the inverse of a function, say for example for f of x equals x plus 6 over 2, remember this is like y here, so y equals x plus 6 over 2. So to find the equation of the inverse function, I'm just going to flip-flop the x's and y's and then solve for y. So I'm going to have x equals y plus 6 all over 2. And so now I just need to solve for y. So we can see here I'm going to multiply the top or both sides by 2. So that means the 2's will cancel out here. So now we've got 2x equals y plus 6. And now my last step to isolate y is to subtract 6 from both sides. And so now I've got y equals 2x minus 6 is my inverse function. But I should write it in the proper inverse function notation so that I can see that it is indeed the inverse of f of x. And so the notation for that is going to be, instead of writing y equals 2x minus 6, to write f and then a -1 exponent. So that reads as the inverse of f of x equals 2x minus 6. And we can verify for ourselves that that is indeed the inverse, because like I said over here, whatever works as an xy ordered pair in my original function, if I take that output, that y coordinate, and plug it into the inverse, I'll get my original x value. So let's say I plugged in 0 into my original function. So f of 0, 0 plus 6 is 6, 6 divided by 2 is 3, so I get 3, meaning I get 0, 3. So that means if I plug 3 into my inverse function, I should get 0 as an output. And indeed, we can see that here. So I've got, if I plug in 3 into my inverse, 2 times 3 is 6, 6 minus 6 is 0, so I indeed get the original output, same output as my original input. So I've confirmed for myself with a quick check that these are indeed inverses. For the second one here, I'm going to do the same thing. So I'm again going to think of this as y equals the cube root of 1/3 x plus 3. So I'm going to flip-flop my x and y. I'm going to flip-flop my inputs and outputs. So I'm going to have x equals the cube root of 1/3 y plus 3. And now I need to solve for y. So the first thing I'm going to do is I'm going to go ahead and cube both sides of the problem. So to get rid of that cube root there. So I get x cubed equals 1/3 y plus 3. So the cube root and the cube cancel each other out. At this point, there's a couple different ways I can approach things. I'm going to go ahead and multiply everything by 3. I know I'm going to have to do that eventually. So I'll just do it right away. So I get 3x cubed equals y plus 9. And so now my last step is to subtract 9 from both sides to isolate the y. So we get y equals, but instead of writing y equals, since I am finding the inverse of my original function g, I'm going to write it as the inverse of g of x, so with that -1 exponent there, equals 3x cubed minus 9.